Damiano Anselmi dell'Università di Pisa, dopo quantum fields versus strings, loops, and all that. That's from quantum gravity.
Thank you very much. So quantum gravity is the attempt to reconcile two radically different visions of reality, the deterministic one and the one ruled by uncertainty. Because in classical physics and in quantum gravity, and in gravity in particular, general relativity, matter follows precise deterministic paths and space and time curve smoothly. But we know that ultimately nature is fundamentally unpredictable. It's ruled by uncertainty, so to speak. Both have been experimentally confirmed to remarkable precision, but they contradict each other at a deep level. And so at the heart of quantum gravity lies the challenge of building a coherent picture of nature that works when both gravity and quantum effects are strong. And one example are black holes. I will not talk about those. The most important example for me is the primordial universe. Over the past decades, the major approaches that have dominated the search for quantum gravity are string theory and loop quantum gravity. String theory attempts to describe particles and forces as vibrations of tiny one-dimensional strings embedded in higher dimensional spaces. Loop quantum gravity tries to quantize space-time itself. There have been many other approaches to solve this problem, but I would like to point out that all of them have two features in common. One is that none of them follows a path that led to the greatest success in high-energy physics, which is the standard model of elementary particles. And the other is that none has made a single testable prediction. And what is the problem? They suffer from infinite arbitrariness because they are not constrained by anything. Not by data, because we don't have, not by experiments, because we cannot make experiments in quantum gravity, and not by the past. So you can propose holograms, you can propose strings. That sounds kind of gratuitous to me. So for these reasons, I and other researchers, some of whom are here at this conference, have decided to continue along the path of quantum fields because it has been the path that led to the quantization of the other three interactions of nature, quite successfully. So is gravity special? No. Why should it be? That's a bet, a hope. It may work or not. But there is no hope that anything else can work, in my view. So this is the only hope. And hope is that if you follow the path that was successful for the other interactions of nature, you are sufficiently constrained so as to have one answer, one candidate, and make predictions that can be possibly tested within a reasonable time, and if you are lucky, within our lifetime. So first of all, it's clear that you need something new, a new ingredient, to inject into quantum field theory to cover the last mile separating gravity from the other three interactions. The same way as you needed something new for the standard model. For example, in the case of a standard model, you needed intermediate bosons and then the Higgs boson, and they were spectacularly confirmed. Here you need something newer because the tricks that worked in the past are not sufficient. So I will tell you about my candidate for the new ingredient, which is a new type of intermediate boson. And the fact that the most interesting thing is that quantum field theory left room for it. And it is built on the concept of a purely virtual particle, which is a particle that is always offset. So it doesn't exist as a particle. It's purely intermediate. It's an intermediate boson that's always intermediate. It's not a resonance. Something else. And then I will tell you about the theory of quantum gravity that you can build on it and its main prediction regarding primordial cosmology, which is the tensor to scalar ratio within this window that you can see. There have been 4 formulations of purely virtual particles, or fake particles, photons, whatever you may want to call them. I will talk about the third one, which is purely diagrammatic, and I think it is also the clearest one. So let me start from quadratic gravity, the theory that has been already mentioned in the previous talk. And I stress that this is not the theory, it's just a starting point. Because this theory, they call it interim theory, is not acceptable, not even as a classical theory, because it is a higher derivative theory. So you have the cosmological term, the Hilbert term, the Starobinsky term. That makes a non-renormalizable theory, which you can use at low energies pretty much as you can use the Fermi theory of weak interactions versus the standard model. You need something else, and this something, however, which is y squared to make the theory renormalizable, makes the theory non-unitary as well. As this is what you find if you treat it as you would normally do. Namely, this is a Lagrangian, you have Feynman rules, you have vertices and propagators, and there is a spin 2 massive field whose kinetic term is multiplied by a minus sign. So that would be an unacceptable particle, a ghost. So this theory contains 3 particles. One is the graviton, one is the Starobinsky, spin 0 scalar, and then you have this spin 2 that you must treat in a special way that I now explain. And then consistency with cosmology puts a bound on this mass, which is the mass of this extra particle. So this is not the true classical action, but it is the starting point, because we have to deal with the issue of unitarity. So what we can do with this action is take the Feynman rules, build the diagrams, and build the S-matrix as you would normally do. You want the unitarity relation, or like this, if you split 1 and IT, I prefer to split S as 1 plus V to save some i's around. And you can prove that in this case you do not have unitarity, but still you can have a very useful identity which is called pseudo-unitarity relation, where in between the product T dagger T or V dagger V you have not the identity but a matrix C which is diagonal and has several plus ones and several minus ones, which signal the presence of ghosts. So this is where you break unitarity. What do you do then? The idea is that the quantization procedure doesn't end there. You have to make some extra mile, and by that I mean that this S-matrix that you build this way and does not satisfy unitarity is not the S-matrix of the physics of quantum gravity. But it's a starting point to build the S-matrix. So now what I want to do is to build all the functions of S you can construct by means of diagrams. Commonly we use Feynman diagrams. The diagrams you are familiar with and correspond to in-out correlation functions or time-ordered correlation functions. You are familiar with Keldysh diagrams, in correlation functions. You may be familiar with Kapkowski-Weltman diagrams, which are those that you use to study the unitarity equation precisely because they are made of 2 parts. One is conjugate of the Feynman diagram, so it is anti-time ordered, shadowed normally, and the other one is a normal Feynman diagram. And the product in between the 2 matrices is represented by cut propagators. I will tell you about those in a moment because they are crucial, and those are purely on shell. So let's study the most general diagrams you can build, and for that you need the usual propagators, the usual vertices as in Feynman diagrams, and just one extra ingredient, which are cut propagators. And you can expand an arbitrary function of the S matrix in powers of S, so you need products, S times S, etc. And so you have diagrams where you have Feynman parts, let's say, and in between the products are cut propagators that have this form. Why? Because if you take the Wick theorem, you'll have a correlator of two free fields, product, not time-ordered product. This is what you get. Namely, you have something that's purely on shell. Given that you have something that's purely on shell, you can use it by subtraction to define something that's purely off shell. And there is a magic formula that I now show you, where you can subtract all the on-shell contributions of a particle inside diagrams, and this way you turn it into something that is purely virtual. So basically, the problem is that in the pseudo-unitarity equation you have a wrong matrix in between, which is not the identity, but it contains many plus ones and several minus ones. You replace it with your preferred projection, A, where you have a subset of the pluses, plus ones, and zeros everywhere else. And then I can show you that there is a matrix formula where the new identity is very similar to the one you had, but instead of the matrix C, which had dangerous minus ones in between, you have the matrix A, which has only plus ones and zeros. And then you use that as a projection. You project the amplitude, you project the subspace, and you get a projected amplitude, a projected S matrix, and in that subspace you have unitarity. So that is the idea. So, as Vali mentioned earlier, I agree with him, a theory with ghosts is a theory with ghosts. You cannot do anything about it. You have to switch to a different theory, because even if they decay as Lee and Wick proposed, this doesn't solve the problem. They're still there, like the muon. It's not that the muon is not in the standard model. You really need to switch to a different theory, and the projection that I mentioned is what does the job, because you cannot go backwards. When you project, there is no way to go upstairs again to the parent theory. There are many, many parent theories that give the same quantum gravity theory I will describe. And so you can start from quadratic gravity because it's simple, but there are many others, there are infinitely many others. So I insist on this because if you want a theory with no ghosts, you really must switch to a different theory. It's not enough to change the correlation functions of interest, in, out, whatever. This just changes the reference frame. You really need a point of no return, and that is the projection. It's like projecting away Fadeev of ghosts. The difference here is that you do not have a symmetry, like the gauge symmetry, that allows you to have unitarity after the projection. But I showed you that if you change the whole diagrammatics, you can achieve a similar result with some prices to pay that I will mention, which can be, however, paid. So, for example, if you go backwards, there is no way to apply the formula backwards. You cannot recover time ordering. You definitely have non-time ordered correlation functions. Let me give a couple of examples. At the tree level, the answer is ambiguous, because if you take out the on-shell part of a propagator, you just have the principal value. Some people in the past, like Bolini and Rocca, Bolini is the one of the dimensional regularization, studied this kind of propagator in Feynman diagrams, and this is not what I'm doing, but interestingly enough, in their paper, they were interested in looking for non-existent particles. So the fact that they were searching for the same entity, although they didn't find it, was quite amazing to me, to realize that other people wanted to find something similar. So, for example, in the bubble diagram, you have, in my case, you cannot change the propagator. You change the whole diagrammatics, and the bubble diagram is a sum of two diagrams, and it is written like here. It's a principal value of something. It is not the integral or the product of two principal values that would violate unitarity. Instead, this one doesn't. Now, in this case, as I told you, the classical theory is not this one. This one is not the classical theory because it's unacceptable. What is the classical theory? It's made of the three diagrams where you have this intermediate boson that is integrated out with the rules, the diagrammatic rules that I told you. Because you can only integrate it out. It never goes outside. You can not integrate it out, doesn't make any difference in the end because it's your choice. But if you want, you can take the classical limit and you will not find a classical theory, you will find a classicized theory, which is a sum of a local part plus a number of three diagrams that are non-local and that imply corrections at energies larger than the mass of the particle inside, which would be around 10 to the 13 GeV. Now, if you apply these ideas in the simple background for primordial cosmology, this is the prediction you get for the tensor to scalar ratio. And the prediction comes from the following thing. If the extra mass m chi goes to infinity, you go back to the Starobinski model, and so you have an upper bound for the tensor to scalar ratio, which coincides with the Starobinski prediction. And then you have a lower bound that is due to a certain inequality that you have to satisfy in order to make sense of purely virtual particles in the de Sitter background. So this is a new ingredient with respect to the properties I just mentioned to you, and I have no time to review it here. But once you plug in both, you have a narrow window. So today we are one order of magnitude away from this upper bound, 2 orders of magnitude away from the lower bound. Probably in 10 years we will know the answer, and probably at the beginning the error will be not enough to discriminate between Starobinski and the window, but moving forward with precision, it will be possible within our lifetime to know where exactly R is in this window. You can push the calculations even further and work out spectra to the precision you want and make predictions for the next centuries. I want to stress that here you can make predictions because of the fact that the theory is unique. You just have one theory with one additional parameter, m chi, but even if it's arbitrary, due to this inequality, you can constrain the prediction to lie, in the case of R, for example, within a relatively narrow window. So this is how the method is powerful. So you can study the running of coefficients, the running of running, and maybe with a lot of effort, it will be possible to test also those predictions. Now, I was not completely satisfied with this idea because there is always the possibility that you have a very nice idea for the S matrix that works only for the S matrix. And quantum field theory is not just the S matrix. Quantum field theory is a full evolution operator, U, between arbitrary initial and finite states. And more recently, I wanted to study quantum field theory off-shell. Because physics is not on-shell. This is a rough approximation. If you want to determine energy with exactly infinite precision, that would take eternity. So the S matrix is between minus infinity and plus infinity. And by the way, let me stress that string theory is on-shell only, which is enough for me to discard it, because I don't understand how you can claim that the theory of everything can be only on-shell. So I don't regard it as people present it as the most beautiful theory of everything. I just think that it is the ugliest theory of nothing. So we want to study the evolution operator, which is e to the minus iht. By the way, this is crucial for unitarity in quantum gravity, because in quantum gravity you have a cosmological constant, and in the presence of a cosmological constant, you do not have an S matrix. So you cannot talk about an S matrix, strictly speaking, in quantum gravity. If you want to talk about unitarity in quantum gravity, you have to build this operator. Otherwise, it's a rough statement. So let me tell you what happens when you do this. You can find it in these two papers. Quite interesting, because you have to reformulate quantum field theory completely in terms of coherent states. It's quite instructive. I cannot go into the details, but you can do it perturbatively. You have diagrams between arbitrary initial and finite states at a finite interval of time. Instead of comparing minus infinity and plus infinity, you have something more realistic. And on an arbitrary finite compact manifold, space manifold. And then this is the conclusion. The conclusion is that you can do everything, and you can generalize purely virtual particles to the operator U, and you will be able to satisfy this property. U dagger equal 1. You will not be able to satisfy the group property, which is quite expected, because if you are able to satisfy the group property, that would mean that you can define time for arbitrarily short intervals of time, which is ruled out by the diagrammatics even in the S matrix approximation. So the bottom line is that you have to renounce the notion of time for arbitrarily short intervals of time. How short? Shorter than 10 to the minus 36 seconds. So let me remind you that we know that time makes sense as time up to 10 to the minus 18, experimentally, 18 seconds. There is no measurement of time below that. So it would be a stretch to believe that there is time up to 10 to the minus 36 seconds and below. And according to the theory, you cannot, and you cannot define U as e to the minus iht, so you have to do the things that I told you diagrammatically, Lagrangian approach if you want. The Hamiltonian approach simply does not exist, because that would imply that time is time for arbitrarily short intervals of time. And again, this answers the question that was bothering me a lot, namely being able to talk about unitarity, strictly speaking, in quantum gravity, where, because of renormalization, the cosmological constant cannot be zero. And so you don't need to talk about the S matrix, which does not exist, but you can talk about U, and you can say that the theory is unitary. There are some prices to pay for doing things this way. One price to pay is that at high energies, as I told you, chronological order is lost. You cannot define events below 10 to the minus 36 seconds. You cannot distinguish past, present, and future. You could say the violation of microcausality or whatever. I don't like to use the word causality because I don't really know what it means. But there is another interesting potential observable phenomenon, because this intermediate boson will never show up as a resonance. Normally you have a peak for a resonance, but this is a new type of entity, and you have to remember that the peak region is always non-perturbative, because you have to resign a geometric series, and you can do it only if you advocate analyticity. You cannot advocate analyticity with this diagrammatics. So that is a truly non-perturbative region, and at finite time you can compare rigorously a resonance. Instead of a peak, you have this oscillating behavior. With what you find with this kind of purely virtual particle, which is two bumps, much shorter. So even experimentally you can see the difference. Now, how have been these ideas received in time? Quite positive, I have to say. I'm happy to report that people are much more open-minded than what I expected, because apart from 2 or 3 ideologues, string theorists of course, and quantum gravitists, everybody is open to pay these prices, like accepting that time doesn't make sense for arbitrarily short intervals of time. But some complain that if you violate chronological order, let's say causality, for 10 to the minus 36 seconds, if you boost, you can have absurd behaviors everywhere in a suitable reference frame. That's true, but you can check in the universe. Those reference frames do not exist. You just cannot find them in the visible universe because you have to boost too much. And the objection of some people, like Giddings last year in Stockholm, is that I should not be in contradiction with logic because you cannot be the father of your father. And so I want to insist that we have no evidence that there is logic in the universe. We have evidence that there is an appearance of logic. Many data that we collect and describe. And by the way, we are a product of nature, not vice versa. So logic, words, which are just manipulations of memorized perceptions, come after, reversing the Platonic hierarchy. So let me conclude with some statement that I use in my YouTube channel to describe the quantum world to people. You should always put the quasi in front of every word you use to understand how quanta works. So instead of saying that you cannot be the father of your father, you should rephrase sentences like these by saying that you cannot be the quasi-father of your quasi-father, or even more extremely, the quasi-you, the we function, quasi cannot quasi be the quasi-father, the quasi-your quasi-father. So when you do that, you are much less extremist, and you find that there is room for these kind of ideas. Thank you.
Thank you, Damiano, for talk. Are there questions?
I have a very little kind of question. So in the beginning you mentioned you mentioned a sort of quantum field theory, and one of that was the standard model. And then to tackle this issue of Bohr's and all that, you generalized. So in the standard model, of course, the successor was the fact that the theory without Higgs mechanism is not unitary. So unitarity was used to constrain the standard model. If we give up on that, then of course we are enlarging. Okay. So the question is, how much are we enlarging the possibilities? So if we give up on unitarity in this particular way, and we go back to the construction of the standard model, are we now going to allow more general theories than Higgs mechanism or not?
If you give up unitarity, you say?
In this sense.
I'm not giving up unitarity, exactly, because these intermediate bosons are precisely what you need to not give up unitarity. So you have a unitary theory of gravity that's also renormalizable, but with a new type of intermediate bosons.
Yes, I understand.
Yes.
So then, like different ways of restoring unitarity. Of course, unitarity is a very general kind of issue. My question is, if we relax quantum field theory, how constraining then it becomes if we look at a construction of the standard model?
I don't want to renounce unitarity, so I just don't consider that. For me, it's an absolute.
Not kind of considering it, but restoring it in this more general way.
So you already used a particle even in the standard model?
Yes, we have studied that with phenomenological group in Tallinn. You can do some phenomenology, but the standard model works so well that yes, you can do that. But in quantum gravity, you need. In the rest, you can add. So that's the difference. I can tell you that you cannot do much for dark matter if that's what you are aiming at. Okay, because this is purely virtual, so it doesn't exist. It's just an intermediate thing. But you can do something. But I do not. After that collaboration, I had the feeling that it's. If there is a place of that in the other three interactions, it still has to be found. We didn't come up with. Yes, you can tailor something, but it's due to model building, which I really don't like because it's not very compelling.
And yes, I can make it. I can just speak up. Yeah, and so just to contribute in this, because the what I don't how to say this. I mean, you are saying that. I mean, normally when we build theories, we make the basic assumption is that nature makes sense, that logic exists, right?
No, I don't make that assumption.
No, I understand that you don't make that assumption. No, sure. I understand that you don't make this assumption, so, but then you can do whatever you want.
No.
I mean, what is that control?
This is an example. I have a prediction may be falsified in 10 years. I did my job as a physicist, period.
Yeah, my question is, how can you make predictions if your starting assumption is that you don't stick to the logic?
Logic is a faith. You want to have faith in logic, then you restrict the number of theories that you want to consider.
No, I understand you don't
and you exclude the right one.
No,
this is what string theorists did.
No, I understand you don't believe in logic, but what is that controls you?
Chance.
So you
Quantum chance? I'm a quantum amplifier.
I don't understand. I mean, when you create a theory, normally we have some rules that control.
I don't believe in rules. Whatever. Yes.
No, but then you can do whatever you want. Then you don't have
No. Can I do whatever I want? I can stay here. I cannot disperse myself as a black hole. I cannot just evaporate.
No, I mean in the theory.
Not at this scale. If I were microscopic.
In the theory building. I don't understand then what restricts you to proclaim whatever you want. Because, for example, I don't understand. You are saying time below 10 to the whatever seconds makes no sense.
Yeah.
And at the same time, you say that your theory is unitary all the way.
Yes.
But
because you have to phrase everything in energy momentum
but
space.
These two statements, for me, because you have a black box, you are saying you have a theory with a black box, and beyond that you don't know what
No. Time doesn't make sense.
Yeah,
you can go in energy.
Yeah, if time doesn't.
You don't do scattering in time. Come on. This is ludicrous.
I don't want to.
Your claim is just nonsense.
Yeah, I don't want
you
to
don't use time for microscopic physics.
I don't want to enter in technicalities because at the starting level, I don't understand what is that you are doing. Because you are saying you don't have any rules.
Yeah, I don't have any rules
in
life. You have a faith. Nice.
I do, yeah.
Yeah.
Okay. Thanks.
You renounce freedom. Think about it.
But I wanted to have put a comment. Basically, many quantum gravity processes exist. Now the debate is renormalizability, respecting renormalizability principle or not.
No, this is my debate was common sense. No.
I mean, I'm not entering into the debate, but renormalizability is the principle here. My question is the following. You said prediction tensor to scalar ratio, but there are many models that can give prediction from observational point of view, putting myself in the observational shoes. I think we need more than just the tensor to scalar ratio. It's not enough.
Yeah, I have plenty of predictions that, however, require much more effort. But I want to stress that there is nothing else that gives predictions. Okay, you can have model building. You can have anything you want in cosmology. These are just models that are not renormalizable. I want here to merge cosmology with high energy physics. We had some constraints. They worked. I make a bet that they still work in this case. Then you have one answer. That is the prediction. Everything else, come on. that doesn't raise to the level of a prediction, please. Okay, so this is a prediction. But I cannot make just one prediction, of course. I can make many about the other quantities that I showed you, and they are precise up to 1 part in 1 million. Will we ever reach that precision? Probably not. But as an exercise, I can do that.
Okay. Let's